Swayam Prabha. Digital India. Educated India.
We will continue with work energy relation for planar kinetics of rigid bodies. Here we are going to look at applications of the work energy relations through some problems. This is the first problem that we are going to take, again from the book of Merriam and Craig. A semicircular disc of mass m is equal to 2 kilogram is mounted in a light hoop of radius r equal to 150 millimeter and released from rest in position A. This blue colored semicircular disc is massive, whereas the black hoop is massless, it is light. It is released from this position A, and it is asked if the hoop rolls without slipping, determine the angular velocity omega of the hoop and the normal force n under the hoop as it passes position B after rotating through 180 degree. Therefore, because of the gravitational field, it starts from position A and slightly disturbed, it rolls without slipping and comes to position B. Of course, it will keep rolling, but we are to find out the angular velocity it reaches in state B and the normal reaction under the wheel. It is in a uniform gravitational field, it is a potential field, there are no other active forces, therefore, total mechanical energy of the system must be conserved. A few things to note in this figure, I have marked out the center of mass of this semicircular disc. It is at a distance of 4 r by 3 pi from O. I am taking the potential potential energy datum at the level of the center of mass in state B. In state 1 or in state A, as shown in this figure, the initial kinetic energy is 0, it starts from rest. Potential energy is because of this height from the potential energy datum, which is 2 times 4 r by 3 pi. Therefore, mg 8 r by 3 pi, that is the potential energy in state 1, and that must be equal to the kinetic energy in state 2 shown in figure B plus the potential energy in state 2, which is shown by figure B, and that is 0. The potential energy in state 2 is 0 because the center of mass has reached the datum. Now, kinetic energy in state 2 I have written using this instantaneous center of rotation C, because C point, which is in contact with the ground, this is rolling without slipping. Therefore, this is as if it is hinged there, at this instant it is hinged, there is a instantaneous center of rotation. Therefore, I can write down the kinetic energy as half the moment of inertia of the system about C times omega square. One more thing to note, it is rolling without slipping, therefore, there is no work done by friction. Here we need to calculate the moment of inertia about C. We note that about O, we know for a semicircular disc about O, the moment of inertia through an axis perpendicular to this screen, that moment of inertia I O is half m r square. Using the parallel axis theorem, I can find out moment of inertia about the center of mass. Note the sign, because we always use the parallel axis theorem from the center of mass, and extending this I can find out the moment of inertia about c by again shifting from the center of mass. Ic is Ig plus mass of the semicircular disc times the distance Cg square, mass times Cg square, and Cg is r minus 4r by 3 pi. Actually, this is this distance d that I have indicated in the figure. So, we have Ic, the moment of inertia about c. I plug in all these expressions in the work in the conservation of mechanical energy of the system, and finally determine omega, the angular velocity. So, this is the first part of the problem. The next part asks us to determine the normal reaction on the disk, on the system from the ground. For this, I have to write Newton's second law for the center of mass of the system. Let us see in this coordinate system x y, which contains the center of mass. This is a prismatic body, therefore, our conditions are satisfied for writing planar dynamics equations. Newton's second law for the center of mass reads mass times acceleration of center of mass must be equal to the net force on the center of mass. I have drawn the free body diagram on which I have shown the forces that are acting, the weight, the friction force, and the normal reaction from the ground. Now, what is acceleration of center of mass? This I have to find out. I can conveniently write acceleration of center of mass in terms of acceleration of the center of the disc, AO. You can of course write in terms of point C as well. We have discussed this in kinematics. What is the acceleration of point C? I have written in terms of O. Acceleration of g is acceleration of O plus alpha cross OG plus omega cross OG. The other terms in our grand equation for acceleration drops out because G and O are points on the same rigid body. Acceleration of O is nothing but alpha cross the radius vector. This also we had discussed, alpha k cap cross r j cap. OG vector I can write, and omega vector and OG vector, everything is known. Therefore, I can represent acceleration of point G. This is the final expression of acceleration of point G. If I look at the j component equation, now I substitute this acceleration of point G of the center of mass in the first equation, Newton's second law for G, and look at the j cap equation. Mass times the acceleration is equal to the force in the j cap direction, and we have found omega from our previous step. And from here I can find out the normal reaction. Everything is known, normal reaction can be determined. What is the use of the I cap equation? It involves alpha, the angular acceleration, on the left hand side, because in the acceleration of the center of mass I have this in the I cap direction, and on the right hand side I have the friction force. These are two unknowns. I need one more equation, and that would be the angular momentum equation. We can write down the angular momentum equation, let us say about g, and solve for the friction force and angular acceleration. I leave this calculation to you. Please complete that calculation. It is quite simple, then the answer is quite straightforward. We move to the next problem, again from the book of Merriam and Craig. A small experimental vehicle has a total mass m of 500 kilogram including the wheels and the driver. Each of the 4 wheels has a mass of 40 kilogram and centroidal radius of gyration of 400 millimeter. Total frictional resistance R to motion is found to be 400 Newton by towing the vehicle with the engine disengaged. Determine the power output of the engine for a speed of 72 km per hour up the 10% incline with A 0 acceleration and B with an acceleration of 3 meters per second square. So, this vehicle is moving up the incline, and this is a very important piece of information that there is a rolling resistance, rolling resistance at the wheels. And how is that determined? It is determined by towing this vehicle with the engine disengaged. Thereby you can find out how much is the rolling resistance. We have to find out the power that is generated at the engine, and since we have to calculate power, it is obvious that we have to use the differential form of the work energy relation. The rate of change of total mechanical energy must be equal to the power. Power is contributed by the engine and dissipated by the wheels because of rolling resistance. Let us look at the first case where the vehicle is moving at a constant velocity. If it is moving at a constant velocity, there is no rate of change of kinetic energy, therefore, d kinetic energy dt is 0. Therefore, we only have d potential energy dt. Let us first look at what is potential energy. Potential energy is mgy, y is the vertical rise of the vehicle as it moves up the incline. Therefore, d potential energy dt is mg dy dt. dy dt is the vertical velocity. Therefore, it is a component of this v in the vertical direction. Therefore, v sin theta. Now, power. The source, there are two points at which we have power exchange with the system. One is the engine is feeding power to the system. The other is the wheels where power is extracted from the system. If I want to find out power that is extracted from the system, I must find out the rolling resistance, this vector, let me call it Fr, and dot it with the velocity of the vehicle, F dot velocity, that is power. Now, rolling resistance and velocity are in opposition. The rolling resistance will always act opposite to the direction of motion. Therefore, this dot product comes with a negative sign. This is the rolling resistance 400 Newton and this is the velocity, and negative sign is because the vectors are in opposition. Plus, this is where the second source, I mean this is the engine power, engine feeds power into the system, and that is what we have to calculate. Therefore, that is the unknown, P E is the unknown. I substitute these expressions in the work energy relation in differential form. I have mass, total mass of the vehicle, acceleration due to gravity, velocity along the incline which is 72 km per hour or 20 meter per second, into sine of theta. So, sine of theta can be determined, it is given that the slope is 10%, I can calculate sine theta, and that must be equal to the power. Power is dissipated because of rolling resistance and fed into the system by the engine. Now, it is a straightforward algebra, everything is known, you can calculate power 17.76 kilowatt. We move to the second part of the problem. Here it has an acceleration of 3 meter per second square. Therefore, now kinetic energy is changing. Let us first write down the expression of kinetic energy. Here the kinetic energy contribution comes from the vehicle as well as the wheels, because the wheels have mass and rotational inertia. The translational kinetic energy of the wheels are included in the first term. This term is the translational kinetic energy of the total system. This term is the rotational kinetic energy of the wheels. This is not to be forgotten. Wheels have mass and the inertia properties are specified in the problem. Because of its rotation, it will have the rotational kinetic energy. Therefore, d dt of the kinetic energy will be, just derivate this, mass times velocity into acceleration plus derivative of this, because velocity is changing with time. Therefore, it has a derivative and we get the acceleration into the rate of change of kinetic energy. The rate of change of potential energy is given by the expression that we have derived earlier, and power is of course remaining the same. We have dissipation because of rolling resistance and power input from the engine, and this is the unknown. Power input from the engine is unknown. I have plugged in these values. You can see this: mass times velocity times acceleration. This is the translational part, translational rate of change of translational kinetic energy. This gives us the rate of change of the rotational kinetic energy. This is the rate of change of potential energy, and that is equal to the power. And it is straightforward to calculate that power fed by the engine into the system is 52.03 kilowatt. That completes this problem. We move on to the next problem. Each of the identical solid square blocks is allowed to fall by rotating counterclockwise from rest position shown. The support at O, in case A, if you look at figure A, there is a hinge at O, and in figure B there is a small frictionless, massless, frictionless roller. Determine the angular velocity omega of each block as the edge OC becomes horizontal just before striking the ground. Therefore, we have two identical blocks, but mounting of the two systems are different. The mounting is different. One is hinged at the corner, the other has a roller, and that makes a difference. Let us see the difference. This is in a uniform gravitational field, which is a potential field, and there is no other active force. Therefore, we must have mechanical energy conservation. Things are frictionless, and there is no other external force other than the weight, which is a potential force. So, we have the corresponding potential energy for that. Now, the initial state, at the initial state when it is left, the kinetic energy is 0, there is no motion in the system. Therefore, T1 is 0. Potential energy datum I have taken at the center of the roller or the hinge, as shown in the figure. Therefore, the initial potential energy of the systems is mg A by root 2. A is the side edge of the length of edge of the plate of the block, and that must be equal to the kinetic energy in state 2 plus the potential energy in state 2. Now, kinetic energy in state 2, for this we are discussing this state problem A, the system A. The kinetic energy in the second state, when it has become when the edge OC has become horizontal, I can write in terms of the point O, half the moment of inertia about O times omega square. plus the potential energy in state 2 of the system, this will be mg a by 2, simply because this has become horizontal, and from the datum the center of mass is at a by 2. I o you can calculate, this is using the parallel axis theorem, of course. This is I about the center of mass, this is mass times the shift square. The shift is a by root 2, therefore, a by 2 a square by 2 is the shift square. So, from the center of mass to this point, this is okay. This is the moment of inertia about O. If I plug in all these expressions in the energy conservation equation, I get omega square, and plugging in the values that are provided, I find omega as 4.94 radian per second. This is for the system 1 when it is hinged. This is quite a straightforward system because it is hinged. Let us move to the second system where there is a roller at that corner O. I have drawn the free body diagram of the system in a slightly displaced configuration. The forces are the normal reaction from the roller and the weight of the block. There is no horizontal force because there is no friction and the roller is massless. Energy will be conserved, of course, for this system, total mechanical energy in state 1, which is the figure shown above, and in state 2 when it has become horizontal, the edge OC has become horizontal. Kinetic energy in state 1 is 0, of course, it is released from rest, the potential energy is mg a by root 2. Now, kinetic energy when edge OC becomes horizontal. Now, since there is no force in the horizontal direction, therefore, this block will not have any linear momentum in the horizontal direction, and that will follow from the momentum conservation. It will in general therefore have kinetic energy due to translation of center of mass and kinetic energy because of rotation of center of mass. Here we just know that the center of mass will not have translation in the horizontal direction, but definitely it is moving, and this hinge O is also moving, that corner O is also moving. Therefore, I do not know, I do not have the complete picture of this motion. Therefore, I write the total kinetic energy of the system in terms of the translational kinetic energy of the center of mass plus the rotational kinetic energy about the center of mass. You can notice that I have written it half I g omega square. This is the kinetic energy of rotation about the center of mass, and the translational center kinetic energy is half m velocity of center of mass square. So, this is the total kinetic energy in state 2. Potential energy in state 2 will be mg a by 2 when it becomes when the edge OC becomes horizontal. Now, to know the total motion of the center of mass, we write down Newton's second law. Mass times acceleration of center of mass is the net force on the center of mass, and from the free body diagram we have all the forces that acts on the system. We have weight and the normal reaction, and that must be equal to mass times acceleration of center of mass. There is no force in the horizontal direction. As I mentioned, there is no force in the horizontal direction, therefore, the acceleration in the horizontal direction will be 0. if you integrate this, then you will get a constant, but then because it started from rest, that constant must be 0. Therefore, there is no velocity of center of mass in the horizontal direction, V g x is 0. Now, we have this constraint that the corner O has no vertical velocity, it does not have any vertical velocity. Therefore, there is a constraint that velocity of O dot j cap is 0. Why do I need this? Because I need to find out the motion of the center of mass, the acceleration of center of mass or velocity of center of mass. I need to find that I will express in terms of velocity of O. I have this constraint that O cannot have any component, the velocity of O cannot have any component in the vertical direction. So, V O dot j cap is 0. Now, velocity of O is velocity of g plus omega cross g O. Both these points are on the same rigid body. We have there is no V rel. Therefore, this is the expression of velocity of point O in terms of velocity of the center of mass. Omega is the angular velocity of the body and g O is the vector from the center of mass to the corner. If I take a dot product of this relation with j cap, that is 0, as we have seen, this is the constraint. Therefore, from the right hand side I will get this expression, and therefore, V g in the y direction I can find out. And here this angle theta, this is the angle theta measured from the vertical to this line O g. In state 2, when this becomes like this and g comes here, this theta becomes 45 degree. Therefore, in state 2 theta is 45 degree, that I have used, and velocity of the center of mass in the y direction is minus a omega by 2. Now, I use the work energy relation, I get this, right. I have the kinetic energy, the net kinetic energy, and this is the potential energy. If I use that, I get omega as 6.25 radian per second. This is the angular velocity in the final state of the system. This second case, the system in figure B was slightly more tricky than that of the system A. System A was absolutely straightforward, but in system B, because the roller could roll, therefore, we had all these intermediate steps. So, that completes this problem. To summarize, we have looked at application of the work energy and the energy conservation relations to certain problems. So, with that I will close this lecture.